Hello, welcome to Unit 8A, Telecommunication and Network Security. In this unit, we talk about network security and other security involving digital communication. We're going to be covering Chapter 6. If you've got the printed version of the book, it's pages 515 to 543, 590 to 611, 628 to 657, plus a little bit about VLANs. OSI reference model. It was originally a blueprint for connecting different vendors' communication equipment. OSI started as a plan to get different vendors' communication products to talk to each other. In the 1970s, network protocols were completely different from vendor to vendor. You had vendor lock-in, but absolutely no interoperability. Something like the internet would not have been possible. OSI tried to fix that, but it was taken over, or overtaken rather, by TCP/IP. TCP/IP, a competing protocol stack, sped past it as was a lightweight, easy-to-use set of network functions. OSI retains its value as an aid to teaching about network. It's still an excellent model for understanding communications. It's strictly conceptual at this point, but it's a very good conceptual framework. It divides the communication process into modular layers. In the OSI model, as in TCP/IP, by the way, a message is passed down through the layers from the top to the bottom. Each layer adds information relevant to that layer. Then at the bottom, it gets sent out over the wire or over the air, transmitted. The other side receives it and then moves it up its own stack, stripping off the information that was added by the equivalent layer on the sender side, interpreting that information and sending what's left up a level. Protocols involved at each layer include the physical layer protocols, kind of the electrical engineering side, the transmission media, the signaling, and the modulation. The data link layer, which is the delivery of information from one point to the adjacent point. It's the point-to-point traffic control, as well as how you access the media. How do you make sure that two devices don't talk over each other at the same time, for example, and that if one device doesn't hear the other device, there's some sort of recovery from that. The network layer, how you send the net information to its final destination across many points in the network, how to route packets. It's reading the map of how to get from point A to point B, knowing every freeway you go on and every interchange you get off and exchange to another freeway. It's a route map, really. The transport layer ensures reliable end-to-end communication by buffering packets, making sure they're in the right sequence. If they're received out of sequence, it shuffles them to make sure they're correct, and that sort of stuff. It makes sure that transportation is correct. The session layer makes the end-to-end communication through the network kind of a virtual data link. The two ends think they're talking directly to each other. The session layer protocols make this happen by adding function, adding information, so that the two endpoints are talking to each other properly. The presentation layer handles data formatting, things like character encoding, ASCII, EBCDIC, Unicode, etc., formatting of data, abstract syntax notation 1, ASN1 versus XML, the format for numerics, is the big bit at the one end or is at the other end, etc. And in the application layer is what actually does the work in the network protocol. It actually gives you email, web browsing, and file sharing, and so forth. Now, the application layer provides services to the user. It's what makes the network useful. It's why we have networking. Examples of application protocols include email, Simple Mail Transport Protocol, and web browsing, Hypertext Transport Protocol, or if you're doing things securely, HTTPS, Hypertext Transport Protocol Secure. The presentation layer standardizes the data format received from the application. It packages the format, determines and interprets the character encoding. It presents the information from the application. ASCII versus Unicode versus the old mainframe-style EBCDIC. Graphic formats, you use JPEG, you use TIFF. Video formats, audio formats, and the use of XML and other message formats are actually at the presentation layer. The session or transport layer consists of several different protocols in a TCP/IP system. User Datagram Protocol sends things one packet at a time. Packets aren't connected to each other or associated with the other. It just sort of sprays information onto the wire. The receiving end receives it as it can, and it's up to the application to make sense of it. Certain applications that need to send through data quickly or in large masses tend to use UDP, like streaming audio, streaming video, because you need to get the data through quickly, and if you lose a packet or two here, it's no big deal, as long as it is received promptly and with little latency. TCP is a more controlled method of sending packets back across the network as a session. And you actually have the two end parties performing what's called a three-way TCP handshake to establish the session information you'll use to transport data back and forth. So you actually have a channel set up that's a continuous channel that's built up and brought down. It's extremely reliable, but it tends to take a certain amount of overhead to do. ICMP, Internet Control Message Protocol, just sends short messages about the network status. Is a device up or down? Does the router know if that route is routable or not? It's a way of querying the network and getting a short message back telling you about the state of the network. Applications like ping and traceroute tend to use ICMP. Sessions present interfaces to the upper layers as application programming interfaces. You can write programs that access the session services, involving things like RPC and SQL and so forth. Now, the network layer consists first of routing protocols. The routing protocols are the master roadmaps. They tell the intermediate devices called routers where to send the traffic, how far does it have to go, which freeway off-ramp do you take. The different routing protocols are RIP, OSPF, and BGP. Those are the main ones being used now. RIP is for small networks, OSPF tends to be for larger enterprise networks, and BGP, Border Gateway Protocol, is for devices communicating across the internet. The routing protocols define the traffic map. The routed protocols are the information that is transported end to end, carrying the data with the address on it saying, I'm coming from here and I want to be sent there. Routing protocols are the roadmap that tells delivery trucks where to deliver the data. The packages being delivered are the routed protocols, and like real-life packages, they have from and to addresses, as well as perhaps certain types of handling information. Now, there are two types of internet protocols, routed protocols. There are IPv4, which is a historic protocol. Addresses are 32-bit numbers that are splitted up into what we call dotted decimal. 10.1.1.1, for example, is a dotted decimal IP address. These addresses, the numbers and corresponding dotted decimal representations, are split into network and host portions. Conventionally, for example, in 10.1.1.1, the 10 is the network, and the .1.1.1, it represents a specific host. You can carve out those 32 bits into host and network portions, with the bigger portion being the network, the lesser portion being the device that the information is being sent to. The network portions, of course, are what routers use to determine how to route things. We've got a new improved version called IPv6. Addresses are 128 bits, which is vastly bigger than 32 bits. It allows more networks and devices. Literally every device on the face of the earth can have an independent IPv6 address. It can be routable on the global internet without having to hide behind something else. IPv6 also includes other neat features that simplify other aspects of network operation. A lot of the things added to IPv4 that are kind of kludgy and difficult to run have been improved there. IPv6 also includes some inherent security that in IPv4 we had to use VPN like IPsec to do. Now, the data link layer below the network layer determines communication between immediately adjacent points. This is conventionally consists of two sub-layers. 802.2 is most typically used as the logical link control. It's the top part of layer 2. It's the bit pattern that determines how the two endpoints talk to each other. It addresses point A to point B. It tells point A and point B whether the frame that is being transmitted has an error in it or not, because data can get corrupted on the wire. And it also includes other information about things like frame priority, etc. Now, below that is the media access control sublayer. That's part of the data link layer that tells the device how to get the stuff onto the media. You don't want two devices talking at the same time on most sorts of common media, because then no communication at all happens. So you've got a media access control layer that coordinates who talks when. And those layers are defined by the IEEE as 802.3 Ethernet and its variations, which cover both wired and fiber-based Ethernet communication. 802.11, which is the most common sort of wireless network communication. Your common wireless cards and access points cover this. DOCSIS, which covers cable internet access. If you get your internet access through a cable provider like Cox or something, or Time Warner Cable, DOCSIS defines how you access that media and how you send information across the cable to the cable head end. And in DSL, which is if you get your internet access through a traditional telecom, involves high-speed internet over phone lines and includes various layer 2 protocols, point-to-point protocol over Ethernet, asynchronous transport mode or ATM, etc. This all happens at layer 2 between your DSL modem and the local phone company's central switching office. Now the physical layer, it's basically the electrical engineering behind communication. It's the media. Do you use fiber, optical fiber? Do you use copper wire? Do you use wireless? Do you use infrared, etc.? The modulation, do you use phase modulation, frequency, amplitude modulation, some combination of those? And in the bit encoding, how does a change in modulation generate a 1 and a 0? So it's basically taking this high-speed electronic or optical information and figuring out how you put 1s and 0s into it. Now, attacks at each layer. The application layer, attackers go after security issues involving the application functionality. Things like email, forged addresses, playing games with mail servers, web commerce security, attacks on web services, secure sign-on, etc. occur at the application layer. The session layer has session encryption. Attacks at the session layer can imply modifications to the various packaging formats. You can play games with XML, with character encoding and encoding of various sorts of multimedia format to mess with the session layer protocols. The session and transport layer protocols are typically treated together because, for example, in TCP, they are in fact one layer there. And the vulnerabilities here involve session hijacking, which is impersonation at the session level, taking over a session between two parties and inserting yourself, as well as eavesdropping at the session layer. At the network layer, you have traffic routing attacks, sending traffic through insecure or compromised links, or just trying traffic up in knots so that nothing gets sent anywhere. At several times in the past few years, there have been inadvertent traffic routing attacks where various countries tried to filter or block certain types of internet traffic and ended up messing up global routing tables and shutting off large parts of the internet. It can also involve incorrect or compromised routing updates. You can send bogus information to a router and say, send something a different way. The data link layer can involve impersonation, eavesdropping, and denial of service at the link level. You can wiretap, you can impersonate the endpoint, you can eavesdrop on traffic, and you can basically tell a device, it's no longer in service and shut it down. The physical layer actually involves physical wiretapping and eavesdropping, listening in on a radio signal or tapping into a wire. Vandalism, breaking the actual equipment, and theft of service, using a network that you're not entitled to use by inserting yourself onto the network itself. So for each layer of the OSI model, you've got different types of malicious attacks that you need to guard against. And of course, at each layer, you've got defenses. The application layer includes secure file transfer, encrypted email, application proxies are just a few examples, anything that secures the application functioning. The presentation layer allows you to encrypt and encode at the layer independent of the application itself, such as encrypting XML. There are standards for encrypting that sort of data envelope. The session layer, you can have session layer encryption using SSL TLS. There are also session layer proxies that can filter traffic for security purposes, like SOCKS, which is a good open source one. At the network layer, IPsec virtual private networks are a network protocol. You have firewalls that filter based on the from and to IP addresses, router access lists which perform similar functions, and secure routing protocols that ensure that routers only receive updates that are genuine and reliable. At the data link layer, for wireless, you've got encryption. WEP was a failed early attempt at this. We now have WPA, WPA2, ways to encrypt at the data link layer. You have layer 2 VPNs like point-to-point transport protocol and layer 2 VPN. And then you can use virtual LANs to separate traffic at the data link layer. At the physical layer, you can physically secure the transmission media. You can put your wiring closet under lock and key. There are various sorts of cable that will detect attempts to tamper with the cable or break in it. You can have guards with guns standing over the cabling plant. Those are all methods of securing the physical layer. If you're using wireless, you can shield against that, both deliberate and inadvertent wireless output. All electronic devices generate a certain amount of radio frequency energy, and that inadvertent radio frequency energy can be subject to eavesdropping. In the defense classified information world, there's a standard called Tempest for shielding against eavesdropping on this inadvertent radiation. Also, spread spectrum, which is a type of modulation, can in some cases be used for security purposes. It was originally intended for this purpose, though you do use spread spectrum now for things like Bluetooth, where it's simply a convenient way of allocating radio spectrum to point-to-point communication. It's not intended for security. But if you have a complex enough and cryptographically strong spreading pattern, you can use it as a form of security. Now let's talk a little bit about VLANs. This is a layer 2 type of thing. Now, your typical network, this is a highly simplified version here, is you've got end devices. These end devices have MAC addresses or layer 2 addresses. They're associated with the actual network card. They are also assigned network or layer 3 addresses, IP addresses, this dotted decimal thing. Here you see a very unusual circumstance where the MAC addresses of these all differ by just 1 bit. This is a classroom example, so bear with me. You won't see this in the real world, but it illustrates that the MAC addresses are unique. These devices are all physically plugged in via cable to ports on a switch. Switch port 1, 2, 3, 4. If you go to the back of the switch, you might actually see these things labeled. On port 5, you've got another device called a router. The router has a MAC address as well as its own IP address. These guys are all connected to a switch. A switch is a layer 2 device. So between the devices on the switch, they all communicate using this MAC address. If this device here wants to talk to that device here, it doesn't use the IP address 192.168.1.1. It uses 001D72, etc., etc. So any device attached to the switch can talk to any other device on the network simply by using the MAC address. It's a free-for-all. Well, yes, they can only talk one at a time to each other because the switch ports are dedicated. But it's, you're plugged into the switch. Anyone else in that switch is fair game. As well as the router. If I want to send a packet to the outside, I send it up to the router, and the router says, aha, that's destined for me. It wants to go to an outside network. I'll send it on its merry way. Now, the nice thing about routers is you can have access lists here. Based on this IP address, the from and the to IP address, you can decide whether or not to let traffic go through. That's a very basic security measure. So here we have, the standard sort of network. Any device plugged into a switch can talk to any other device in that switch as long as they take their turn and don't talk at the same time. They talk to each other across the switch using the MAC address, that big complicated hexadecimal thing, 001D, etc. The IP address only comes into bear when it's talking to the router, because the router needs to know your IP address to send your information or forward it outside to the rest of the network. Otherwise, the IP address don't matter. Now, this business where the devices can talk to each other maybe isn't so good for security. Maybe you want to separate devices. Maybe devices connecting to the same switch shouldn't be allowed to talk to each other at whim. You have something called a VLAN that will do that. We have arbitrarily made a red and a blue VLAN. Guess what? This device can only talk to this device using the MAC address, and the same thing here. If this device wants to talk to 192.168.1.4, first off, it has to do it using the IP address, not the MAC address. It has to use the layer 2/3 network address, not the layer 2 MAC address. And then it has to do, in this environment, it has to go up to the router, and the router says, okay, I will send it back to you guys. In the CCNA exam, this is called a router on a stick, because the information goes from the switch to get from VLAN A to VLAN B. It has to go to the router and then back down. But what you've done here is you've separated the traffic out into a VLAN that I call the red VLAN and another VLAN called the blue VLAN. We actually give VLANs numbers. That might be VLAN 1, that might be VLAN 2, for example. But this guy can't talk using the MAC address to that guy. It's got to use the IP address. The other neat thing here is you can filter VLAN to VLAN traffic at the router level. So this is sort of a security measure. It's actually designed to separate traffic based on, common characteristics, and to kind of keep different types of traffic from stepping on each other, and to better organize how you separate out your LAN. But it can also be drafted for security purposes as well. So that, in a nutshell, is what a VLAN is about. And of course, both VLANs can talk to the router and then to the outside world. The router just has a rule to accept traffic from either the red or blue VLAN, and if it wants to go outside, it goes outside. Now let's look at the OSI reference model in TCP/IP, because the OSI model is just for academic purposes, but TCP/IP is actually how the world works nowadays. The physical layers correspond. In a TCP/IP world, you have a physical layer that's pretty much independent of the TCP/IP protocol. It exists underneath it, but it's defined by where you plug it into a switch or what wireless frequency or channel you're using. The data link layer is also beneath TCP/IP, but it is defined by the media access control or MAC address. You know how device A talks to device B on the same subnet, talking to the same switch, okay? Once you want to go from a network A to a network B, you deal with a network protocol. And in TCP/IP, it's called the Internet Protocol, and it's defined by network addresses. You then have the session and transport layers combined, and they correspond to either TCP, UDP, ICMP, and a couple of other ones. IPsec is actually another protocol I should have put here. And sessions are defined by ports. You have an IP address plus a port. And the combination of those two, the IP address gives you the network endpoint, and the port gives you the service on the other end that needs to address that session. And then finally in TCP/IP, the application and presentation layers are kind of merged into one. For certain purposes, it's good to separate these, but they're basically considered as one in this network model. Now you've got services that translate between layers. Address Resolution Protocol, or ARP, translates between a network and data link. Dynamic Host Configuration Protocol also does the same. And in the domain name service takes a network address and turns it into an arbitrary name that allows you to talk to the application layer. Domain name services, what do? They resolve host names into IP addresses and oftentimes do the opposite. www.uclaextension.edu is a host name. In order to actually get there, you have to know what the IP address is. You look that up in DNS, you get an IP address, and then your traffic gets routed to the UCLA Extension website. It can also identify the types of servers and services and certain Active Directory Windows services in an internal network. Active Directory makes extensive use of DNS in advertising the different services available to devices in the Active Directory system. Plain old pre-Microsoft DNS, tells you where the mail servers are and a few other significant services within a particular domain. It's used for strictly internal resources as well as public resources. So you can have DNS to figure out where things are inside your network, and you obviously have to have DNS to figure out where things are outside their network. The namespace is split into zones, and each zone is managed by a DNS server that is authoritative to that zone. If you ever register an IP address, that registration process, by definition, gives you authoritative name servers that contain the zone for all the stuff under that domain name. So, if somebody's looking up www.myveryownwebpage.com, there is an authoritative DNS server for www.myveryownwebpage.com that lists all the stuff there. Other domain name servers may copy that information and cache it for the purpose of convenience, for speeding and expediting things. So secondary DNS servers may get a copy of all the stuff via something called a zone transfer, which is just a major dump of all of the DNS information about a zone. Attacks against DNS include modifying the hostname file, fake DNS replies. Somebody says, give me the IP address of this really important banking site, and a fake server can say, I'm the IP address, here it is. Here's the IP address, and that IP address is actually to a hacker site. So if you can fake a DNS reply, somebody thinks they're talking to their bank, they're talking to a hacker site, and the hacker site gets all their credentials. And that's the last point. You can redirect traffic to an attacker site by resolving a legitimate name to an attacker IP address. The way to deal with some of these attacks is by split DNS. You want to separate your internal and external DNS servers and keep the internal names away from outside inquiries. So you have one DNS server for the inside of your network and another one that just handles externally accessible names, and the two never meet. Address Resolution Protocol. It maps a layer 2 or media access control address to a layer 3 IP address. If you're talking on that subnet I showed you earlier, and you need to send information to an IP address on your very network, you'll send out an ARP request. Who has IP address such? And then the recipient will say, I am, and here's my MAC address. And it's like, great, we're on the same subnet. I have your MAC address. Now we can talk. ARP only acts within a subnet. It doesn't cross routers or other network boundaries. So it's an extremely local sort of name lookup. Attacks can involve traffic interception and rerouting. You can send traffic elsewhere by, faking ARP replies, and you can perform a man-in-the-middle attack. You can say, hi, I want to talk to the router, and go to the outside world. And then the evil host on that subnet says, I'm the router, send your traffic to me. Your traffic goes to the evil host. The evil host eavesdrops on the traffic and then sends it out to the legitimate router. Man in the middle. Dynamic Host Configuration Protocol assigns layer 3 IP information to systems as they join a network. If you don't define upfront what your IP address is, your subnet, who your DNS server is, who the router to get to the outside world, your so-called default gateway is, your device will send out a request asking for this stuff, and if you've got a DHCP server, they'll say, hi, welcome to our network. Your IP address is this. Your subnet mask, your network is this. Your default gateway, the router that you use to get to the outside world, is this IP address. And by the way, your DNS name and your DNS servers are such and such. So, you plug your laptop into a network at some visiting location, and they give you this stuff because, hey, you're a visitor. We want to make your life comfortable and tell you everything you need to know to use our network. Devices basically lease an IP address out of a pool. That lease can be very short or very long. Other network information is also assigned, like the gateway, the router to get to the outside world, the subnet mask, what network am I on, and how many bits in my address are in a network versus how many bits are in the host name. Now, there are attacks in DHCP. Obviously, if you plug any system into a network and it gets assigned an address, that means a rogue system owned by Mr. Evil can be plugged into your network, and that system will work just as well too. So you got to keep track of what's on your network if you're using this. You can also set up rogue DHCP servers. Someone can pretend to be your DHCP server and then tell legitimate clients, hi, I'm your gateway. Send your traffic to me if you want to talk to the internet, and then pass that through. So you can route traffic to compromised gateways by setting up a rogue DHCP server. By the way, these are sometimes inadvertently set up when people plug in unauthorized wireless access points and stuff like that into a network. These devices are oftentimes by default configured to be DHCP servers, and having this unauthorized DHCP server on your network will absolutely wreak havoc. And that's it.